Good evening, Supriyo. You need to unmute.
Yeah, I look like Andhadhun guy. Harish, we just received an email from Taluja.
I think we will discuss. This is recorded, so we'll discuss it later. It is being recorded. Yeah.
I'm responding to him anyway.
Yeah. Okay.
Okay. So one thing that I wanted to ask Dr. Tendul. So I after the Thanksgiving, I mean, vote of thanks, not Thanksgiving, sorry. So I end up meeting, or what I say, like good night, I should say, or somebody else will say anything.
I think you can give a vote of thanks, and then Dr. Tandel can say bye.
Okay. All right.
Yeah, because he is the host, so let him take that opportunity to start and end.
Okay. All right. All right. Then I'll come back after a few minutes. Thank you. Meeting, or what I say, like good night, I should say, or somebody else will say.
You can give a vote of thanks, and then Dr. Tandel can say bye.
Okay.
Yeah, sure.
Yeah, because he is the host, so let him take that opportunity to start and end.
All right. All right.
So, Supriyo, how are you?
I'll come back. I'm fine.
Yeah, sure.
Why?
Dr. Tandel, I think your YouTube and both things are.
Yeah.
So you can.
Yeah, I will shut off my YouTube.
Yeah, you just keep on mute.
Yeah. So now you can hear me fine, right?
Yeah. And the thing, you please clear the some kind of marks are there on the screen.
Yeah. I cleared that because annotation was enabled for the participants. So now I will stop sharing and start sharing again, so that I have disabled the annotations. So now it should be okay. I'll stop sharing and start sharing again.
Yeah.
So now it should be okay.
Yeah, it looks good.
Yeah.
Okay. Then I'll come back after some time.
As it turns out, Harish, sure, Supriyo. Yeah, as it turns out, Harish, I mean, I had thought of this possibility that our speaker and guest of honor know each other quite well, and they are very happy to be sharing the stage, so to speak. And so they will maybe have a chat for a few minutes before we begin.
Sure, that's always good, actually.
Yeah, absolutely.
So already you had just communicated with them just now, or?
Yeah. Just a couple of hours ago, both of them I was in touch with.
Sure.
And they are going to join a few minutes before 8:30.
Okay.
We have a lot of participants. Let me make sure that I understand when they are joining.
Yes.
So all of you have joined on both Zoom and YouTube. Good evening to all of you. We are not beginning yet, but it's nice to see that so many of you have gathered well in advance of the speaker. So that tells me that you're eagerly anticipating the talk. And so I hope all of you have had your dinner and are relaxing in your easy chairs, so that you can kind of learn about the origin of our universe, and then the most recent discoveries on gravitational waves, and so on. So I am sure that this will be an interesting talk. So
it is going to be interesting not only for physicists, but I think for geoscientists like us also. We are always interested to learn more about origin of universe, black holes, and probably I think for each and everyone, even right from young children and aged people, all are interested to know how this entire story is running actually.
absolutely. And specifically, since you mentioned earth sciences and geosciences, the discovery of gravitational waves is basically a kind of looking for some kind of a seismic wave. So, which of course in geoscience, you're always kind of, that is one of the main things that, or one of the important things that is being studied. So in gravitational waves, basically they are looking for a very, very small signal. And the idea is to kind of figure out how to disentangle the signal from all the other noise. And so I think that's quite interesting.
See, these all are indirect ways. Like in geosciences, we know much about the earth and interior structure of the earth because of seismic waves, right?
Right.
So, lot of science, geoscience, physics, chemistry. I'm a geologist, but my research is basically on chemical aspects. Then I do some kind of biological work in organic part. So it is kind of multidisciplinary for each and every one of us.
Right, right.
Yeah.
And cosmology is, which is the kind of area of expertise of our speaker. So that is something that I think is kind of sometimes borders on the philosophical side. Sometimes, how did everything begin? How did the universe and how did we come into existence, and so on. So I think that's a subject that is perhaps appropriate for the first lecture in the series, because how did it all begin? So it is with this lecture that it all began.
You know, now in my MOOCs program, my first lecture itself is about origin of Earth and water on Earth. Okay.
Okay.
Right. So then, like how whether other planets has water on it, or why Earth as a planet is unique. Then second one, I'm talking about origin of life. So whatever the subject, the fascination always goes about the origin of certain things, right? Right from life to water or planet, whatever you talk.
That's right. Yeah.
We all are connected.
Yeah,
Ananda.
absolutely.
Good evening, Anand.
Good evening, good evening, everybody.
Rename yourself. You are using Aru Bhabhi's
yes,
name.
yes.
So we have very good combination. We have physicists working on black holes or gravitational forces, origin of universe. Then we have astrophysicists studying stars to learn more. Then we have geologists who are having idea of how things went around after the formation, right? So by studying the past of Earth or geological history of the Earth, so many things are there within our group. Yeah.
Yeah. Okay, so we have our speaker, Professor Ashtekar. Can you hear us? Professor Ashtekar, can you hear us? Your mic is muted.
Okay, I tried to join with my iPad, but because that's a better place, but I could not do it. So I guess I just have to pull up my file on the PDF here. So here the pointer is not so good, but that's life. Okay.
Sure.
Okay. So
good morning to you.
Good morning. Yeah, I mean, good evening to you, I guess. Yeah, right.
Yeah.
Just 1 second. Let me just get my files here. So I'm going to try to share screen and see if it works. Can you hear me?
Yeah, we can hear you.
Yeah, okay.
You can end your screen sharing. Let's try.
Yeah.
I'll do that now. It says the host has disabled the participant screen sharing.
No. Can you please try again, Professor Ashtekar?
Yeah. Yeah, I get the same.
Just one moment.
Yeah.
Just let me check. Sorry.
Yeah.
Yeah, can you try now, please?
Yeah, you may have to make me a co-host. Yeah, I think it worked. Thank you. So you should be seeing part of my screen. Do you see that?
Yeah, we can see part of your screen. That's right.
Sounds good. Now the point here is that I should put this away. So you see the whole screen, or how should it?
Yeah,
okay?
we see the whole screen. Yeah.
Okay. I had to do a few things. And do you see my cursor?
Yeah, we can see your cursor as well.
Okay, that's good. Okay, then I think this okay. I can just use this one then.
Professor Godbole was in touch with me a little while ago. So,
yeah.
So she is very keen to meet you and speak with you.
Yeah, certainly.
Yeah.
Yeah, I've known her for decades, so it's a pleasure for me to. Yeah.
Yeah. I'll just check whether she has joined.
Okay.
Not yet.
Okay.
We'll just wait for her for a couple of minutes.
Yeah, absolutely. Absolutely.
Yeah, sure.
Dr. Tandil, now you can share our PPT about FR.
Yeah.
So once we start, yeah.
Yeah. So Professor Ashtekar, if you don't mind, can you stop screen sharing from your side? I will share my screen because there are some slides that we would like to show to the audience.
Sure.
So we're waiting for Professor Godbole, all of you. She's the guest of honor. But perhaps while we are waiting for her, let me just go over some of the things related to the...
Sujit, I'm having trouble logging in.
Okay.
I have logged in from somebody else's account because I don't have a Zoom account. And it's asking me to log in a Zoom account, which I cannot do.
Okay. Yeah, sure. So we can see you. Wonderful.
No, but this I cannot work this way. So I have to log out from here, and I have to try if I can do it from my computer. Okay. So you have to wait.
Okay.
Because what you have done is that the things you have sent require a Zoom account, and I do not have a Zoom account.
No, you don't need a Zoom account, Professor Godbole. You can just use the meeting ID and the password to log in without... Yes.
I tried that. And it asks me to sign in.
Okay.
For the past 10 minutes, I've been trying.
Okay.
Just 5 minutes, I will try through somebody else's Zoom account. Just you wait.
Sure.
For 5 minutes.
Sure.
आता बंद करू कसं करायचं बंद हा लीव मीटिंग ना इकडे हा
ठीक आहे तुझा अकाउंट वापर
हा
Yeah, Dr. Tandel, it's always required to have a login ID.
I have been using Zoom for a long time without creating an ID. So just the meeting ID and the password, and if you put in, then you just have to put in your name over there without having an account. For the first few months, I used Zoom without an account actually.
Okay.
I think it's in the setting where you have to set that login is not required.
Yeah. And one can even log in with a Google account if you wish, without creating a Zoom account.
Okay.
No,
I was
Sujit,
not aware.
Sujit, what I mean, you have to, because you have created the meeting. So
yeah.
In that setting, you have to unset it. That login is not required. If you have set it, then whoever joined, he or she has to require the login.
Yeah. So actually, that's what I have done. But let me check once again. So, Professor Ashtekar, while we are waiting for Professor Godbole, perhaps I will just tell you a little bit about our association.
Yeah, please.
And since there's a number of people in the audience, so I could maybe Harish, since we will wait for Professor Godbole to join, and in the meanwhile, I can start telling the people about the UFA.
Yeah, please. I think that's best use of the time.
Yeah, so best use of the time, perhaps. So, okay. So I guess you can see my screen. Just one moment. So the UFA is a national association of faculty in STEM appointed under the Faculty Recharge Program of the University Grants Commission, UGC India. And there are 6 streams in the UFA. Under sciences, we have biology, chemistry, earth and physics, earth sciences and physics. Under technology, we have engineering and also mathematics. And we have a pan-India presence with around 155 faculty in universities or institutions across the country, as you can see from the map here. So the UGC Faculty Recharge Program, or FRP scheme, was launched by the UGC as a flagship scheme for augmenting internationally competitive interdisciplinary research and teaching resources in the STEM domain in Indian universities. The UGC recruited fresh talent with international exposure committed to innovative teaching and cutting-edge research. The recruitment process was very stringent, and less than 3% of the applicants were selected. And the placement was done through a nationally conducted competitive process. And we have been placed at both central and state level universities in India. So I will just enumerate some of the achievements of the UGC FRP faculty to date. We have been in service for a relatively short period of time. The senior most among us have been in service for 7 years as FRP faculty, and some as little as 2 years. So during this time, we have had a lot of publications, as you can see from here, more than 1,900 peer-reviewed journal publications from among 155 faculty who have joined between 2013 and 2018, including papers in science, nature, physical review letters, etc. And we have obtained a significant amount of extramural funding to the tune of 84 crore rupees. And this has been independently obtained from external funding agencies. And in this fashion, we have contributed to strengthening the research environment and infrastructure in the university system. And many of us have made extensive contributions to laboratory development, including setting up new laboratories with the grant funding that we have obtained. And in terms of mentorship, many of us have collectively guided thousands of undergraduate and master's students and hundreds of doctoral candidates in their research work. And I would like to emphasize the laboratory development part, because traditionally the Indian university system laboratories have not been that strong, barring some exceptions, and that is one place that we have contributed. So the University Faculty Association was set up with the vision to promote collaborative research in the STEM domain. The idea was to have science for society outreach for humanity and national welfare, and to initiate collaboration between academia and industry. So our mission is guided by the motto Jnanam Paramam Dhyayam. The UFA strives to empower pedagogical qualities of teaching and research for enhancing the international standing of our country in the STEM domain. And we have many of my colleagues have initiated a number of activities. I will just go through some of them. So we recently had a webinar series on the new education policy, which was just launched by the Government of India. And we had several distinguished speakers speaking on the new education policy, as you can see from the posters here. And also, we had a national webinar series on women in STEM, that is the connections between academia and industry. And we had, again, several webinars related to that, and distinguished speakers as well. About 4 webinars have been completed until now. And today we are here for another new initiative that we have launched, that the UFA has launched, which is the online colloquia by Indian origin scientists, or short is OCOs. So this will be a continuing monthly series of online colloquia, which will be delivered by eminent scientists of Indian origin, who are presently based in institutions overseas. So the idea is to promote exchange of information, enable networking, and have collaboration between the resident Indian, the Indian at heart scientific community. So we will have colloquium style lectures by experts at the cutting edge of their respective fields. So we expect that this will stimulate interest among the students, help outreach, and encourage interdisciplinary research. So at this point, so this is the brief introduction that I wanted to give you about UFA and the program that we are initiating. So I will stop here now. And I will ask the president of our association, Dr. Harish Gupta, to say a few words.
So, good evening, everyone. And Professor Ashtekar, good morning to you in USA. So, this is Dr. Harish Gupta, Assistant Professor at Department of Civil Engineering, Usmania University, Hyderabad. And,
hello. Hello, this is just to check if you can hear me now.
No. Oh, we can hear you.
We can hear you, Professor Godbole.
Yeah. So, I take this opportunity to welcome our speaker, Professor Abhay Ashtekar, and our guest of honor, Padma Shri, Professor Rohini Godbole, my FRP colleagues and participants who have joined through various modes. Today, our country is celebrating Parvasi Bharatiya Divas to recognize the contribution of Indian diaspora spread across the world. And we have taken this opportunity to launch this particular webinar series. We Indians are known for our wisdom, knowledge, capabilities, and currently over 1 million Indians from science field, engineering, then your medical fraternity, and so many PhD students are working abroad, and they are contributing to India or mother nation back through various means, which includes research collaboration as well as mentorship, and many more are willing to do so in the future. So we FRP faculties, we have worked abroad early in our career, and then we returned back to join and serve our country as UGC FRP faculty. So many of the Indians who are working into the top positions abroad, now we are through this webinar series, we are planning to approach them, because some kind of we people in India, we need some kind of motivation. And then there's a definitely knowledge gap, there's a perception gap, and then we need to motivate our students as well. So taking these points, to take these points forward, we have launched this particular series. So it will help FRP community and students to associate with foreign, our Indian scientists who are working abroad. It will give scientific exposure. It will give some kind of scope of collaborations, and it may help students to have better career opportunities in future. They may have some kind of postdoctoral research opportunities as well. Besides, our scientists peer working abroad will have exposure to, we people are a dedicated group of people. So the people who we are going to invite, they may have some kind of interaction with people like us. And because we are a group, so a lot of opportunities are there, and we are also looking for a lot of opportunities. So in that direction, today we have taken this small step, and we are planning to continue this webinar series for long, and we want to make it more prominent in time to come. This is first talk in this series, and we are delighted to have our guest speakers and guest of honor today with us. Thanks, everyone. Now I request Dr. Hemlata to take over and take further proceedings. Thank you.
Thank you, Harish. I'm Dr. Hemlata. I'm deeply honored to cordially welcome our speaker for today, Professor Abhay Ashtekar, and our guest of honor, Professor Rohini Godbole. The University Faculty Association and the UGC FRP community are very grateful to both of you for sparing time for this event. We are glad to have both of you here today for this special occasion. We have a limited number of people in the Zoom meeting. However, this event is being live streamed on YouTube, and I can see that we have about 100 viewers already. Let me introduce Professor Godbole, who is our guest of honor today. She is professor at the Center for High Energy Physics, Indian Institute of Science, Bangalore. She has worked extensively on different aspects of particle physics phenomenology over the past 3 decades, authoring more than 280 research publications in refereed journals and archived e-prints, many of which have been highly cited. She has been associated with many institutions: IISc Bangalore, CERN Geneva, DESI Hamburg, ICTP Trieste, TIFR Mumbai, and the University of Mumbai, to name a few. She is a fellow of Indian Science Academies and has edited Pramana, the Indian Journal of Physics, for a long time. She has received the INSA Satyendranath Bose Medal for Theoretical Physics. She has also been recently conferred a Padma Shri by the Government of India. I now request Professor Godbole to address the participants.
Okay. So, friends, thank you very much for putting up with the vagaries of Zoom. I'm sorry that I was not able to join from the beginning. And even now, I'm just been able to join from a tab. So bear with me. I might just shift around somewhere. So first and foremost, let me just say that it's a great pleasure to be here on the same, even if virtual dais, with Professor Abhay Ashtekar, whom I have known for now a few decades. I guess I knew him for a long time, but he and I got to know each other. He came to know of me only about 2 decades ago when we were together on a council of one council of Ayuka. I have attended actually many functions which have speaker and a chief guest. Sometimes I have been a speaker, sometimes I have been a chief guest. But for a real function, the chief guest really has one big advantage. That is, he or she gets to sit in the front row. And for a speaker that you're going to hear today, namely Professor Ashtekar, this is a real advantage, as he speaks not only with his words, but also with his face and conveys information in an excellent manner. Thanks to the virtual media that we have, now all of us, not just the chief guest, will be able to enjoy this. As you've been already told, today this function is a colloquium, first in the series of colloquium that is being organized under the initiative of the UGC FRP University Faculty Association. I congratulate them on this nice effort. As far as I know, there are about 150 faculty members in this association, and they're working all over India in different places. Sujit, who is one of the coordinators of this event, is in fact used to be a student in the University Department of Physics at the university when I used to be there. So that was the second reason why I agreed immediately when he asked me to be the chief guest. As I said, first, of course, being on the same stage with Professor Abhay Ashtekar. So I kind of asked him, what is it that you would like me to talk about? And I have followed his advice, and I'm going to give you some thoughts about what I think about research, because as I know, the faculty recharge program, all you faculty have actually a special responsibility as well as a special privilege, that the idea is that your research will add very positively to the achievements of the universities, whichever departments you are recharging. But before I begin with that, I should also say that yes, I have had the pleasure of being associated with this FRP program once during the interviews. And I have at that time seen the high level of the applications or applicants that the program receives. I had at that time, in fact, reservations because the program really did not have clear guidelines about how to relax age limits for people who have taken a break. And most of the time, people who have taken a break happen to be women. And I would say that this experience was, in fact, one of the many triggers that I had, as a result of which we finally suggested, and the suggestion has been accepted in the Science, Technology and Innovation Policy 2020, which just came out, which draft has been released just a few days back. And this has a suggestion and statement about considering the academic age in case people have break. So I imagine and hope that in the future rounds of FRP, this kind of suggestions will get included, and that would help the scientists who are applying for the FRP positions and have taken a break on the way. As I said, most of the time, people who are taking a break happen to be women. So now let me try to go and give my own thoughts about what I think, or what in my experience research has been, and how one can function and do research of good quality, which will bring happiness to the person who conducts the research, and at the same time bring credit to the university departments where one is associated. So one of the things that one has to realize about science, that science does not always progress in a straight line. Standing on the shoulders of giants, the community in a particular subject embarks upon investigations into mysteries of laws of nature, which, based on making progresses in what is the available information in a subject. And then that process is like going up to a mountain and climbing it up sometimes. But what happens sometimes is that after you have reached that stage, you have climbed that mountain, you have solved some problems, then you find that once you have reached that peak, the vista that is offered by that peak actually raises further questions or shows up more peaks which are lying beyond the peak that you were trying to reach. On the other hand, it also tells you that the peaks you were thinking were closer are much further apart. The questions they require more input to solve them, which means that the way science progresses is by finding answers to questions, which answers themselves lead to newer questions, and that's how the journey of science continues. Now, the important question that one has to ask is, how do individual scientists like you and me forge their own path in this big journey? I mean, people who are path leaders actually show us the big path, but then we have to see how to journey on those paths. And in that case, I would say that research really essentially becomes seeking answers to questions in your own subject, which arise in your mind when you try to get a deeper understanding of the subject. I must say that my description gets shaded by the fact, affected by the fact that I happen to be a theorist, but I think one can rephrase it exactly also for the experimental sciences. And I find that the main difference between, doing research in your PhD or doing research in a postdoctoral position, as many of you have done before joining the FRP positions, it's really, after this stage is over, you have to learn to ask your own questions. And it's important that one figures out one's own, one finds what one wants to do without, sort of following some fashions, but more looking at what is it that my mind is burning? What is it to know? What are the questions to which I would like to know the answers? So it is very, very important to set very clear goals. And while finding correct, good questions to ask, what is meant by good questions? Firstly, they should not be trivial. That means that the answer to the question, no matter how small, will somewhere contribute to a progress. It may be just a piece of a little grain of sand that gets put on the Ramasetu that the monkeys were building for Sri Ram, but it has to be some small contribution. And actually, the biggest happiness in the career of science research that comes is when you find one new thing and then you say, aha, others didn't know this, I can show them. And this can happen only when you ask your own questions. But it is not a very easy thing to figure out which questions are the ones that are sort of solvable. I mean, you can ask very deep questions. How did the universe came into being? There are some answers to this, but I mean, you can ask a very great sounding question, but whereas there is no idea how one will go about solving it, that is also not very good. It should also not be a very trivial question. And then once you ask that question, you have to figure out and define the framework. What are the tools that I'm going to require? Are these tools available to me? Supposing I'm an experimental physicist and I need to do some experiments, particular type of experiments to get the answers that I'm seeking, then is it possible for me to be able to stitch together the apparatus? Is it within my reach? These are the kinds of questions that you have to ask. And if you don't have the tools, but still you are very, very much passionate about getting that answer, then you try to go about and say, how do you build those tools? So basically this is how it moves. And all this, I can say this, that the new ideas or the new questions come to you only when you first get a good and clear understanding of the theoretical and experimental situation in the subject of your interest. And you have to try a variety of ideas. So to me, sometimes I feel that doing research is like sifting sand on the seashore, and then somewhere you find that a ray of sun just shines, and you find that the grain of sand that you actually had in your hand or have in your hand, it happens to be a diamond, a little diamond, may not be a huge diamond. And that's the sort of day, and that's the point for which you kind of live. But for this to happen, you have to try out a variety of ideas on for sides. And somewhere so you have to keep on. Also here, you have to, as I said, you have to first figure out how to pursue an idea, how to try to get an answer to the question. But it's also important to realize at a certain point when to give up, when to realize that this is not possible to answer this question within the resources, intellectual or experimental resources that you have. It's also important that you have to be really perseverant. That is, of course, you need the original independent thinking, which will give you these brilliant ideas, but you also need to be ready to work quite hard. And all of us don't have the intellect of the big giants, but most of us have the ability to be able to work hard. And if these questions are something that you have thought of yourself, that are the ones for which you really want to know the answers, then I can say that the conditions with the physical obstacles that do arise, and particularly in the university structure in India, there are a variety of obstacles. But I think once your mind is set on doing something, those obstacles don't really hurt as much as they would otherwise. If you are not passionate about what you are doing, they might deter you more. But if you are passionate about what you want to do, then these physical obstacles won't very much deter you. And that's, I hope that all of you would have fun on this path of research as much as I have had. So I wish you all a lot of luck and all the best in your further journey in science.
Thank you, Professor Godbole, for your deep insights. Thank you, madam. It's always been wonderful to hear encouraging words from you. As you know, now we are on to what we are eagerly waiting for. As you know, our speaker today is Professor Abhay Ashtekar. He is the director of the Institute for Gravitation and the Cosmos, A1 Pew Professor of Physics and holder of the Eberly Chair in Physics at Pennsylvania State University, USA. Before joining Penn State, he was the Erastus Franklin Holden Professor of Physics at Syracuse University and Professor Chair de Gravitation at Paris. He was awarded Dr. Rerum Naturalium Honoris Causa by Friedrich Schiller University, Jena, Germany in 2005 and by the Université d'Aix-Marseille to France in 2010. He is the past president of the International Society for General Relativity and Gravitation. He was elected to the US National Academy of Sciences and has won the Senior Forschungs Prize by the Alexander von Humboldt Foundation and the Einstein Prize by the American Physical Society. He is the fellow of the American Association for Advancement of Science and American Physical Society, and of the only 51 honorary fellows of the Indian Academy of Sciences drawn from the international community. He has held the Cramer's Visiting Chair in Theoretical Physics at the University of Utrecht, the Netherlands, and Sir C.V. Raman Chair of the Indian Academy of Science. He chairs the International Advisory Committee of the Indigo Consortium in connection with the LIGO India initiative. Professor Ashtekar will be speaking about black holes, Big Bang, and gravitational waves, illustrations of paradigm shifts in fundamental science. Before Professor Ashtekar begins his talk, all participants are requested to mute their microphones. Those participants viewing on Zoom and YouTube can type their questions in the chat box at any time and should clearly mention their names and affiliation. Dr. Tandel will be conveying these questions to the speaker. Without any further delay, let us begin the session which we have been eagerly waiting for. I request now Professor Ashtekar to commence his talk.
Thank you very much. Let me start sharing my screen. I hope it works. Can you see my screen now?
Yes, sir, we can see.
Wonderful. And do you also see my cursor, the thing that I'm moving?
Yes, sir, we can see.
Fantastic. Okay, so it's a pleasure to sort of follow Rohini Golbole. I don't say professor because I've known her for decades. And in fact, I had heard about Rohini even when I was a graduate student. And she gave us really, particularly to the young scientists in FRG, the real words of wisdom, which I hope you'll remember for a long time. And what I'll try to do is really follow her up by presenting some illustrations of paradigm shifts in fundamental science. You're all of the age and you're all of the academic level in your careers that you are probably eager to make these paradigm shifts. And I just want to sort of tell you how things have happened. And this is not totally trivial because the way that the scientific history is written is quite different from actually the things happen, the way they happen. So I've chosen some examples from my own expertise in gravitational physics. Black holes, I put black holes first because that is what the Physics Nobel Prize of 2020 was for black holes. Then Big Bang and the gravitational waves, and these are the illustrations of paradigm shifts in fundamental science. I realized just now that it's already 9 o'clock at night for you, so I'd first hope to cover all these topics, but that will take me about 50-55 minutes. So I'll stop after black holes and I'll ask you, and maybe I can just skip the cosmology, the Big Bang, and just talk about gravitational waves if it is really getting late. Okay, so so goal of this talk is really a rather general discussion on the theme of paradigm shifts in basic science. I know there are many of you who are really in technology and not in fundamental science, but I think these general ideas that I'm talking about, these examples that I'm giving, really apply to technology as well. It's just that the details are different, but the general lesson is really the same. And therefore, I'm just illustrating these lessons by examples drawn from my expertise. And I would like to bring out three main points. First, what is now considered as commonplace knowledge was not at all so just a few decades ago. In fact, much of the scientific community at the time was probably thinking in almost the opposite direction. Now, this is something that you should bear in mind as you do your work or as you choose your problems, as you choose your areas, that the consensus today may not at all be where the answers are. The real answers may be in a completely different direction. So you need really courage to really not to challenge the conventional wisdom at times. Secondly, I think it would be nice if people were to mute their mics because there are echoes. The second is precisely because these paradigm shifts are so startling at first, they take decades to get settled and become common pool of knowledge. So in the meanwhile, you should not get frustrated. So you really need patience. And the last thing is that the factors driving or slowing the process of this paradigm shifts process, they're quite varied. It is all presented as being in retrospect as a logical stream, and of course it was inevitable, but it's not at all so. And there are many factors that come into play in this paradigm shifts, as we'll see, and not all of which are scientific. And therefore, you really have to have the maturity to accept this fact. So these are the lessons. And now I'm going to start talking about the way that the paradigm shifts occur. And actually, I want to talk about black holes, the Big Bang, the gravitational waves, but all of them really have to do with general relativity. And since this is not a physics audience, I would like to talk about a few slides on general relativity and the curious fact about how general relativity evolved. So I think all of you have heard in your high school days or early college days, the Newton's ideas really formed the basis of physical sciences for 3 centuries. And we are most familiar with these ideas in the Newtonian paradigm. In this paradigm, space-time is an inert backdrop. It is really sort of a stage or arena on which things happen. The actors are everything else, like planets or stars or elementary particles and forces of nature. So those are the actors, and space and time is just some backdrop on which these things happen. And in Newtonian gravity, in Newtonian theory, gravity is a force between these massive bodies. And the point about gravity that is so special is because there is a universal force. The Newton's law of gravitation, doesn't depend on whether the object is silver or gold or whatever. The force is always just given by, m1, Newton's constant times m1, m2 upon r squared. And that is the universality there. And this paradigm reigned for over 200 years, but it was shattered by Einstein's general relativity. Space and time fused into a 4-dimensional continuum. And this was very counterintuitive. And geometry in general relativity, geometry of space and time, is now promoted to physical dynamical entity, just like matter. So just like you can act on matter, like a chair you are sitting on, you can push the chair, or if you can jump on Earth or you can throw a ball on Earth and the ball bounces. So Earth reacts back, so to say. So in the same way, space-time geometry is a physical entity which can be acted upon and then it reacts. And this is a radical shift in the description of reality, that space and time is no longer inert backdrop or a stage on which things happen, but it actually space and time geometry joins a troupe of actors. There is no spectators, if you like. There's no everything, including space and time, are part of the drama. They are the actors in this universal drama that is unfolding in nature. And this shift is absolutely essential when gravity is strong. And therefore, and in fact, in Newtonian theory, gravity is universal. The force is the same between all these objects, but that is even sort of more universal because it is absorbed into the very geometry of space and time. And space and time is where everything happens, and therefore gravitation is elevated to a new level of universality. So how does this general relativity come into account, come about? And really, Einstein worked tirelessly for 8 years for this to happen. But just before these 2 years, these 8 years, in 1905, many of you who are not in physics would have heard that Einstein discovered special relativity. And it is in this special relativity that already the Newton's notions of space and time were dethroned, and space and time fused to form a 4-dimensional continuum. And an immediate consequence of that is the famous Einstein's equation, E = mc squared, the equivalence between energy and mass, which, for example, governs nuclear reactors or the sun. Sun is converting energy into the mass into energy all along, and it's sustaining our life here. But then 2 years later, in 1907, Einstein realized that there is a fundamental tension between these notions of spatial relativity, this four-dimensional fusing of space and time, and Newtonian theory of gravity. And the reason is basically because in Newtonian theory of gravity, force between any two objects is transmitted instantaneously, whereas in spatial relativity, the causal signals from one object to another can propagate only at most at speed of light, and therefore this transmission cannot be instantaneous. So there is a fundamental tension, and the resolution that came up was Einstein started thinking that just as we have a new theory of space and time, perhaps we also need a new theory of gravitation, so a new theory of space, time, and gravitation, a theory that will absorb in it ideas of Newtonian gravitation, but made compatible with the notions of space and time that were given to us by special relativity. So Einstein was working on this, and during this phase, 1907 to 1915, Einstein was in 1913, a few years before that, was in Switzerland, in Zurich, in the Polytechnic. And then Max Planck, who we see here, came to Zurich to convince Einstein to go back to Germany. And they made a very generous offer to Einstein to go back to Berlin. And then at the end of these administrative procedures and making the offer, Max Planck asked Einstein, what are you working on? So Einstein said that, well, he thinks that there should be a new theory of gravitation. Newtonian theory of gravitation is inadequate, and we need a new theory that makes gravitation compatible with the notions of space and time that were given to us by special relativity. And Max Planck was a leading scientist. He's the founder of quantum mechanics. He was a leading German scientist, international scientist at the time. But even he said, as an older friend, I must advise you against trying to do this. For in the first place, you will not succeed. And even if you do succeed, no one will believe you. And this really is the first part of my message, that the mainstream ideas may not be compatible with your thinking, but you should have the courage that Einstein had. Einstein, fortunately for us, persisted. And in these 8 years and 2 years after this conversation with Max Planck, he gave the final formulation of general theory of relativity. So what happens in general theory of relativity? Well, gravity fuses into space-time geometry. So gravity is no longer a force, and space-time is no longer an inert background or a stage. The gravitational field is encoded in the very geometry of space and time. Basically, if you have a massive object, it's depicted here in artist's depiction, like a sun or something like that, then it bends the fabric of space and time, the geometry of space and time. And then smaller objects like Earth, like the planets, which are moving in this gravitational field, they would actually be moving. They will be trying to go as straight as they can, but because space-time itself is bent, their trajectory looks bent from the Newtonian perspective. And thus gravity is actually encoded in the very geometry of space-time. And this is possible. Why gravity can be done and not electricity and magnetism or strong or weak interactions. And that is because gravity is omnipresent. You cannot shield gravity. No matter where you are in the universe, gravity cannot be shielded. On the other hand, electromagnetic forces can be shielded. There are lamps which shield, for example, magnetic fields. This is just not possible for gravity. And it is non-discriminating. It is universal. It acts the same way on all objects. And that's why it's just like geometry. Now, general relativity, space-time is bent. And then matter tells space-time how to bend or how to curve. The heavy body bends the fabric of space-time. And then the curved space-time tells matter how to move. And geometry is intertwined with matter via Einstein's equations. Einstein's equations tell really how matter bends space-time. So this discovery of general relativity came in November of 1915. And then a day later, Einstein wrote after submitting the paper, Einstein wrote to Arnold Sommerfeld, who was a theoretical physicist, in fact, the first theoretical physicist to occupy a major chair in Germany. And he was in Munich. And Einstein said, during the past month, I experienced one of the most exciting and most exacting times of my life. True enough, also one of the most successful. This is a bit like what Rohini was telling you about. Then when you discover something and sun shines on it and you see that it is a diamond, and that is a thrill, and that is what Einstein is talking about. Of course, Einstein was not just a little grain of sand that he discovered, but he really created a paradigm shift. And then he goes on to explain why, the marvelous thing is that it is not just new conceptual framework, but really explained as a certain mystery about the orbit of Mercury, which had been mystery for a very long time. So when Sommerfeld received this note, Einstein, he was surprised by exuberance of Einstein, because Einstein was generally very understated. And he sort of wrote back saying, really? I mean, is that important? And then Einstein wrote back to Sommerfeld saying that, well, of general theory of relativity, you will be convinced once you have studied it. And he was absolutely right. Those of us who study it just marvel at the beauty, at the depth, at the way it synthesizes a very, very broad arena of phenomena. We really marvel at it all the time. But even after 1915, it took 4 years and totally non-scientific world events for general relativity to be accepted as a revolutionary paradigm shift. And these world events were the First World War. At the end of the First World War, Arthur Eddington, who was a British astronomer, led a mission to test general relativity through bending of light, one of the predictions of general relativity. And the prediction of general relativity was that light should be bent twice as much as what Newton would have predicted. And Einstein's theory was verified. And at the time, the world was really hungry for something that is wise. It was really completely fed up by the horrors of war, which are caused typically by divisive politics. And the world was really completely fed up with that, and seeing a light in which a theory, which was really created by German physicists, was verified by British scientists, really showed, something that how science and technology transcend these stupidities of humankind that arise due to violence and war. And because of that, I think it is true that Einstein was really catapulted into world fame with Eddington's discovery. So in November 10, 1919, here is a heading of the New York Times: all lights all askew in the heavens, men of science more or less agog, or results of the eclipse observation of Eddington, and so on. And the point nonetheless is that immediately Einstein became a household name. So you see, Einstein had this persistence, this courage in believing in his ideas, even though celebrated physicists like Max Planck were really discouraging him. And he finally proved it. And yet he had to wait 4 more years for the recognition to occur. Among the scientists, on the other hand, the recognition occurred right away. And Hermann Weyl, famous mathematical physicist, really said something which we feel even today, more than 100 years after the discovery of general relativity. And what we feel is that it is as if a wall that separated us from truth has collapsed. Wider expanses and greater depths are now exposed to the searching eye of knowledge, regions of which we had no idea that they existed. We did not even have a presentiment. And this is what our own hero, Subramaniam Chandrasekhar, wrote about general relativity, that when Henry Moore, which was a famous sculptor, who's one of the famous pieces is in the University of Chicago campus. So when Henry Moore visited the University of Chicago some years ago, that is Chandra, had an occasion to ask him how one should see sculptures, from afar or from nearby. Moore's response was that the greatest sculptures can be viewed, and indeed should be viewed, from all distances, since new aspects of beauty will be revealed at every scale. And then Moore cited the examples of Michelangelo, and this is one of the famous sculptures, La Pieta, with the Virgin Mary and Jesus Christ up here. And as that in this sculpture, you see beauty, new aspects of beauty revealed if you look at it closely, and if you then go further and further. And the same thing is true with general relativity. Now, there are many of you are in technology, and you would ask a legitimate question, saying that, okay, this is really beautiful that Einstein did all this work. He really completely shattered the paradigm of space and time and gravitation, created this beautiful theory. And this theory is really very important when there are black holes and Big Bang and such thing. But does it really matter to us on practical terms? Should we care about this at all? And we should, because as I say at the bottom of that slide, fundamental laws of nature always matter. And here is an example that effects of both special and general relativity are critical for the global positioning satellite system. And why should we worry about global positioning satellite system? Well, because we carry a cell phone in our pockets, and our cell phone tells us, for example, maps, directions, and so on, tells us where we are, our location. But that requires this global positioning satellite system. There are signals going in back and forth between the satellites and our cell phones all the time. And that is how our position is determined. But if we ignore special and general relativity, this what seemingly abstract ideas, but integral part of physical reality, if we ignore these things, then within 2 minutes, literally 2 minutes, the GPS system, the global positioning satellite system, localization error will go to about 23 meters. Now, 23 meters is a huge uncertainty. And therefore, pilots use GPS to land your airplanes, and airplanes will fail to land on runways. So you see, even these abstract paradigm shifts matter in a way that is really practical. It's just that you cannot predict it ahead of time where it is going to matter. What seems like fantasy today is often essential for tomorrow's technology if grounded in this, if this fantasy is grounded in solid fundamental science. So this is the first part in which I told you about the one revolution and one paradigm shift that occurred, and how all kinds of events were necessary for this paradigm shift to be completely accepted. Now I talked about black holes. And I chose to first to talk about black holes because black holes are really, that is where the just 2020 Nobel Prize was given. So it may be fresh in most people's mind. And black holes you can think of as being regions where like end of space and time, that is okay, regions of space and time from which even light cannot escape up here. So here are two pictures. One is a depiction, both of this is an artistic impression, and this is just cartoon, but drawn from physical results. And here there is a central black hole, and there's a companion star, a large star, and matter is falling into the companion star. And as the matter falls, it creates X-rays and gamma rays, and those are really sent out. And we see this. We don't see this process in detail, but we see what is emitted. And now, of course, and the second one is really, I'll come back to that, is really the black holes, which were actually detected by the LIGO scientific LIGO-Virgo scientific collaboration. There's a laser interferometric gravitational observatory. I'll come back to that a little bit later. And so nowadays, to most of you read about black holes, and they're widely recognized as engines that drive the most energetic phenomena in astrophysics and in the universe. But this was not always so. Again, black holes were a true paradigm shift, and they were not accepted. And the way that finally the acceptance came is also quite interesting. So to begin with, let me begin in a retrospective thing. And as I said, in October 2020, the Nobel Prize was given by Theoretical Foundation for Black Hole and Supermassive Compact Object at Galactic Center. And it was one half of it is given by Roger Penrose for the discovery of black hole formation as a robust prediction of general relativity, and the other half jointly to Reinhard Genzel and Andrea Ghez for the discovery of a supermassive compact object at the center of our galaxy. So let me begin first with the observational part, because that is more intuitive about the supermassive compact object. So here is a picture of part of a Milky Way, sort of center of a Milky Way. This is about a light year. So this is the distance traveled by light in 1 year. And the compact object is up here. This is about a 1/1,000,000th of a light year. So that's why it's so small. 1 million, you can hardly see it up here. So there is this compact object, which everybody believes to be a black hole. It's called supermassive because the mass is huge compared to the sun's mass. It is about 4.3 million solar masses, and it is called Sagittarius A star or SGRA star. And now, how do you know, since this is so tiny and we cannot see it, black hole is, light cannot escape from it. So how do you know there's a black hole? Well, what we can see is stars which are going around, and there's a whole bunch of stars in this diagram, which was from the Nobel Prize, as you see at the bottom of the slide up here, the Nobel Prize announcement. They selected one star, which is most prominent, which is S2, it's called. And this star is going around this central object, and this is its orbit. People have made measurements of this star from 1992 to 2018. So, over a long period of time, we're seeing this star going around up here. And the point is that you can also observe the orbit of the star and deduce that there is a central object with a certain mass, and that is, and it's very, very compact, and that is how one knows that there is a compact central object. This orbit is such that at the closest encounter, when S2 is somewhere here, for example, closest distance up here, it is about what is called 1400 times the Schwarzschild radii. If you like, the radius of the black hole is 1400 times that. And the velocity of the star, believe it or not, is about 60th of the velocity of light. So this is really very, very careful observations that have to be made. They have to develop new technology. So technology is really important here. Infrared technology have to be developed to look at these such stars and to conclude that there is supermassive black hole in the center of our galaxy. Amazingly, the prediction about such predictions, the way that that you can deduce something which is, you don't see this central object, but you can deduce its presence by looking at the orbits of other objects, other stars which are going around it. This idea was actually already appeared in 1784, more than 230 years ago, 236 years ago, based on Newton's law of gravitation. And this is a paper by John Mitchell in the Transaction of the Philosophical Society. He said, if there should exist in nature any such bodies, we could have no information from sight, because they will be black, because their gravitational field is so strong that the escape velocity is bigger than or equal to the escape velocity of that of light, and therefore nothing can escape. And yet, if other luminous bodies should appear to revolve around them, then we might perhaps, from the motion of these revolving bodies, infer the existence of the central ones with some degree of probability. And so that is exactly what was done before. And this would seem to indicate that perhaps black holes, in Newton's theory of gravity, also has black holes. And people widely believe this, even in physics circles, and this is incorrect. So let me explain it. This reasoning behind the fascinating conclusions of Mitchell and also Laplace, you have heard of Laplace equation, Marquis de Laplace. He wrote 2 treatises on celestial mechanics, and there he had a very clean discussion based on Newtonian gravity about objects for which the escape velocity would be bigger than the velocity of light, and therefore light could not escape from these objects. But this is conceptually flawed, because even if light cannot escape from this object because the escape velocity is larger than the speed of light relative to the object, because all speeds in Newtonian gravity or Newtonian physics are relative, we could still see this object. How? There could be light falling on this object by coming from elsewhere. For example, we see the moon, not because the light that is emitted by the moon, but by light that is reflected by the moon. And the light is really coming from the sun, and that is reflected by the moon, and that is what we see. In Newtonian theory, as this light falls on this object, it would be accelerated. So when it hits the object, its speed would be bigger than the escape velocity of light, escape velocity of that object. And therefore, when it is reflected by conservation of momentum, since its velocity would be bigger than the velocity of escape velocity, it would come out. And so we should really be seeing these black holes by reflected light just as we see the moon. There really are no black holes in Newtonian physics, if you look at it very carefully. We need both an absolute speed of light and gravity for black holes to exist. So here is a picture that came from Penrose's papers and that was selected by the Nobel Committee. And basically, time is running vertically upwards, so we are not used to seeing such pictures normally. This is not just a space diagram, but time is running upwards, and this is space. Of course, one dimension is suppressed because it's a really four-dimensional continuum, and here one is trying to look at it as a two-dimensional, three-dimensional continuum. Time upwards and two x and y directions, if you like, of space up here, and one dimension is suppressed up here. And so you may have a star, for example, a collapsing star, which is depicted here as a little disk. In reality, it will be a ball, three-dimensional ball. Here it is a two-dimensional disk. And it collapses, and it really, when it collapses, what happens is the gravitational field becomes so large that here we got light cones. That is to say, light emitted here will propagate, will go out in this particular direction. These light cones tip over, and therefore all future light rays actually are trapped in this region. So there's a trapped region here from which light cannot escape. And that is what is predicted by general relativity, because space-time geometry is dynamical. Over here, the light cones of space-time geometry are all upright. Over here, they're bent because space-time geometry is dynamical. Space-time geometry can be bent by heavy object. And therefore, in general relativity, there are regions in which light is trapped in an absolute space, in an absolute sense. It does not matter what the velocity of the object, of the observer is, irrespective of the motion. So if you send in light, it cannot be reflected back because it's completely, this region, light is completely trapped. And that is because velocity of light is absolute. It is not relative to this object. It's an absolute constant of nature. So both curved space-time, the bending of space-time is essential for it, and constancy of velocity of light is essential here. It's the same diagram, which I'll explain a little bit in a minute. Now, so let's go back to history. And the simplest black hole solution, as a solution to Einstein's equation, was discovered by Karl Schwarzschild while he was serving actually on the front during the First World War. But a clear black hole interpretation had to await several decades, both because leading researchers did not understand the interplay between geometry and physics very well. And basically the point was that people thought that the surface of the region where light is trapped was a singularity, because if you look at the solution that Schwarzschild found, it becomes singular. It becomes, things become infinite here. So they thought that this is unphysical. This is something that is not physical. And they thought that what Schwarzschild found was a solution without any matter. And in real world, there will be matter here. And therefore, Schwarzschild's solution would not be valid, and there will be no such region in which light is completely trapped. People thought about this for a long time. It was really pioneering work of Belgian the physicist and mathematician Lemaitre and American scientist relativist Finkelstein that showed that the blowing up, the divergence that occurs in this solution is physically spurious. It is just that the light is trapped up here. So there, I mean, now one understands this so-called causal structure, the light cone structure of the space-times very well. And we know that light is trapped irrespective of how it enters and irrespective of the motion of the observer. For everybody, according to general relativity, light is completely trapped here. Now, this curious history of black holes. So Chandrasekhar discovered, this is the young Chandrasekhar, he discovered between 1931 and 35, very steady stream of papers, that what happens to the fate of the heavy stars. If you have a sufficiently heavy star, what would happen to it? Now, a star like our sun, for example, is shining, is stable there, and so on and so forth, just because the gravity is trying to pull the particles in the sun towards the center, collapse, and make it into, if you like, a black hole. But there is a nuclear reactions which are going on. And because of this nuclear reaction, we have emission of light. So, and this light which is emitted creates a certain pressure, outward pressure. And there's a balance between this outward pressure of radiation and the inner gravitational pull that actually causes an equilibrium state. But what happens if a star actually runs out of its nuclear fuel? What I said about the sun is true for all stars. The stars are shining because of nuclear reactions inside them. So what will happen if it really runs out of the nuclear fuel? Then there is only gravity, and then the gravity will prevail. And the star is sufficiently heavy, then in fact, it would form a black hole. And Chandra sort of made this pioneering discovery. And again, for you guys, young guys, this is really very thrilling that he actually, the first calculation he did was during the boat trip to England when he went to Cambridge at the age of 20 to do his PhD. And then in 1939, Oppenheimer and Schreier considered spherically symmetric collapse to a black hole in general relativity. And they actually showed, I mean, basically this picture that I had previously, this picture I had before. So they took a spherically symmetric star. They solved Einstein's equation both inside and outside. They matched the solutions, and they showed that with respect to outside, light could never come out. Light is all trapped in this region. And that's why if they showed that Einstein's theory actually does predict that if there is no pressure on the star holding it steady, if it has run out of nuclear reactions, then the star would actually collapse, and would in space-time region, there would be a trapped region up here. Now, just as a side remark, in 1937, so 2 years before that, there was an interesting paper by Professor Dutt in the German journal Zeitschrift für Physik, and in that he actually obtained the same solution as, I mean, he obtained many things in that paper, but one of them, in retrospect, you can see, is the same solution that Oppenheimer and Steiner obtained in the interior region of the star. But the point is that he never made any contact with the exterior region. It was just a mathematical solution for him. It is not talking about stars collapsing or anything like that. He's just talking about mathematical solution to Einstein's equation, or what happens if you consider spherical solutions, which are dynamical. And so he really has no interpretation about black holes. So I think in some of the Indian press recently, it was said after the Nobel Prize that Dutt actually foresaw the Oppenheimer-Schneider collapse, and I think that is an overstatement. That did not occur. But as you can see here, that there was a general reluctance to accepting the idea that stars more massive than the Chandrasekhar limit have no equilibrium configuration once they exhaust their nuclear fuel. And that is really some cultural thing that I was talking about that prevails, and for good reasons, but you know, the reasons have their limitations. Namely, astronomers prefer a serene, calm universe, not a violent one. And there is a quirk of history also, that the same time that this paper appeared, in 1939, when this paper appeared, the same day, Bohr and Wheeler's paper on nuclear fission occurred, and people were very important. That was very important because Hitler was supposed to be building a nuclear bomb. And also, that was the same day in which Hitler invaded Poland. So this is another example in which completely non-scientific reason can completely, delay the recognition of importance of the seminal work that these people had done. And as you can see, this reluctance in acceptance of the existence of black holes, that continued. Namely, same Eddington and Einstein is the same Eddington who actually had verified the general theory of relativity, and therefore made Einstein a household name. But same Eddington was very reluctant to accept the notion of black holes, and he opposed Chandra's ideas. And even there's a famous sentence by him, which, if some graduate student made such a statement in their comprehensive exam, they would fail the exam. But here was an eminent scientist, the president of the Royal Astronomical Society, making such a statement: various accidents may intervene to save the star, but I want no more protection than that. I think there should be a law of nature to prevent the star from behaving in this absurd way. And of course, it was completely wrong, as the history proved. But, this is a very, very leading prominent scientist saying that. So to you young folks, I would say that, take words that are coming from well-established scientists with a grain of salt. They don't have to be absolute truth at all. And even Einstein, that's why I put these people together. Even Einstein published a paper in 1939, not in such emotional way, it's a systematic paper. And the paper was supposed to be on impossibility of formation of a black hole through gravitational collapse. This paper is technically correct, but he made an assumption that when the star collapses, it happens adiabatically, very, very slowly. And that assumption is violated in the Oppenheimer-Schneider collapse, where in fact black hole is formed. And the Oppenheimer-Schneider paper just appeared just a few months later, showing the black hole formation by spherical collapse. The key word here is spherical collapse, because they were trying to solve a solution of Einstein's equation, and Einstein's equations are complicated, so they could only do it for completely spherical symmetry. And because of this spherical symmetry, there is a widespread belief in the community that this means that typical real stars are not going to be spherical. They're not going to be exactly spherical. And if there is no spherical symmetry, then in fact, the collapse would not occur and black holes would not form. There was even a program by the Russian school, led by Lifshitz. I think many of you know the Landau-Lifshitz book series, by Lifshitz and Kalatnikov, which tried to say that a generic solution of Einstein's equation, which does not have any special symmetries, would not be singular. There would not be black holes in therefore black holes would be not generic at all. And since real stars are not exactly spherical symmetric, their collapse would not produce black holes. But what the 1965 paper of Roger Penrose showed is that without any symmetry assumption, if one accepts general relativity and physically available matter, satisfying so-called energy conditions, then gravitational collapse will inevitably lead to a space-time singularity, and so therefore the black holes. And I should say that in this work, a seminal role, absolutely central role, is played by the equation that was discovered by A.K. Raichaudhuri, AKR, as is fondly known to many people, many of us. And so this really is a seminal Indian contribution, as opposed to that of Professor Dutt's in respect to black holes. This really is seminal. So I just wanted to highlight that. And therefore, in the Roger Penrose's work for the discovery of black hole formation, is a robust prediction of general relativity came from the Raichaudhuri equation up here, and without the assumption of any symmetry, because this equation does not use any symmetry. So what I've tried to do in this part is really to tell you that the revolutions occur, they are very deep, they affect how you think in the future forever. But on the other hand, these revolutions are not immediately accepted. At the time that these paradigm shifts are proposed, most of the community might be completely thinking in the opposite direction, and you need patience and courage to still pursue your work. So this is the first part, and now the black hole is first two parts. Now the black holes are routinely invoked as engines driving the most energetic explosions of the universe, and here I give some examples. So I'll pause here for a minute, and maybe if there are any questions, Sujit can tell me if there are any questions in the box, and I'll take them. And in the interest of time, I'll skip the second part on cosmology and go directly to gravitational waves, which is a much shorter part.
Yeah. So Dr. Suresh from University of Calicut is asking what it actually means that space and time bend.
It just means what it says, namely, okay. It's like, I think it's difficult to visualize in the 4 dimensions. So let me just give you this 2-dimensional analogy, which is given here in the picture of a rubber sheet analogy. So you have to imagine that what happens in reality is 4-dimensional version of this. So basically what we normally think of on a sheet of paper, the sheet of paper, which if we just take, the distance between any 2 points is given just by the delta x, the difference in the x coordinates squared, plus delta y squared. So this distance defines what is one called a metric. A metric on 2-dimensional sheet of paper determines its geometry. So it tells you what the distance between any 2 points is. And what happens in presence of matter is that the distance between 2 points is just not just given by x squared plus y squared. So for example, again, in just 2 dimensions, you can consider it as the surface of a sphere. That is a bent sphere, and the distance between the 2 points there is not given in some simple way like that. The metric of that piece of the distance function, or the metric, is really bent. Or if you like, heuristically, you can see that if you take a 2-dimensional, the surface of a sphere, or if you like, surface of a donut like vada, you can see that it's actually bent. And now it's difficult to visualize, but that is what is happening in 4 space-time dimensions. Another question, perhaps?
There are actually many more questions, but I will ask one brief one from Pawan Maulia. He's asking what you mean by inert background or inert stage.
Good. By inert stage, like in a play or in a drama, right? The stage is given to you, and the actors come, they move around, they do things, but the stage is, the background is just fixed there. You cannot, I mean, the actors don't affect the background, and the background directly doesn't push the actors around or anything like that. But what happens, and usually we think about space and time, because in everyday life has been, space is just sitting and time is just flowing, and it is not affected by anything else. It is just serenely going, time is just serenely passing, and space is just, just given to us once and for all. And the point is that in general relativity, this is not the case. As for example, the sun itself is going around the galaxy, and so as the sun moves around the galaxy, this bending of space is occurring all along. So this bending of space is moving. This little dip that you see up here is actually moving as the sun moves, is moving with the sun, if you like. So the space-time itself is not, the geometry of space-time, I should say, is not an inert, as was believed in Newtonian theory. In Newtonian theory, distance between any 2 points is just delta x squared plus delta y squared plus delta z squared, and that's it. And that is not the case up here. And not only is it space-time is bent, as in the first question, but space-time, where it is bent is actually in general relativity depends on the matter. As the matter moves, the geometry itself is bent. Okay, I mean,
yeah. So there are many more questions, but I think perhaps you may want to take them at the end of the talk.
Yeah,
so
I'll take them at the end also, right? Exactly. So in the interest of time, I will, sorry, but I'll just skip this cosmology part, and I will just talk about.
Maybe Professor Ashtekar, Professor Godbole has a question, if you want to answer that.
Please, please.
She's asking whether you can comment on the ideas that gravity is an emergent phenomenon.
Yeah. So, I mean, I think gravity is an emergent phenomena, personally. I mean, in fact, it just happens, Rohini, that the very last, if you just look at in archives, the very last paper I wrote, the whole reformulation of general relativity I had done many years ago has to do with really thinking of general relativity in the language of Yang-Mills theory. I'm sorry, the question is a little bit more technical than the previous one, so the answer is also a little bit more technical. So the very last paper that I have there, I mean, discusses in precise sense in which gravity actually appears as an emergent phenomenon from this Yang-Mills description. So to begin with, in my formulation, there is no metric, there is no space-time geometry even, and all that is appearing because you are reinterpreting things in a certain way. And loop quantum gravity in particular is based on the idea that gravity is an emergent phenomena. Again, I'll be happy to comment on this at the end when there are question period. Okay. I'm skipping our cosmology part, but I still would like you to just, the audience to perhaps there's a paradigm shift and another paradigm shift that has occurred, which has to do with the new meaning of the Big Bang. And the new meaning of the Big Bang is that most of us now don't believe that Big Bang is really the beginning of the space and time, that most of us in cosmology or working on the frontier regions in cosmology, the very early universe, the Big Bang is not supposed to be an absolute singularity where things completely break down at all. And here's a nice video. I'm suggesting this because it is only It's called before the Big Bang, I think it is called. No, I'm sorry, it's called The New Meaning of the Big Bang. That's what it's called. And in the mainstream cosmology, the Big Bang refers not to the initial singularity, but to a hot phase in the early universe. It is not really the beginning of space and time itself. So there are 6 of us who were interviewed. It's a very short thing, just about, as you see here, it's just about 6.5 minutes. So you might want to just look at that. And the second thing is that what I covered in the first 2 parts up here, and also in the cosmology part, actually. There is a paper, this particular book just came out in this year, 2021. It's available on Amazon, it's very cheap. And those of you who are interested in these ideas, particularly people in physics, but also non-physics people, how our notions of space and time changed. It's called The Origin of Space-Time Physics. I wrote a very detailed foreword to say how this thing occurred. It has papers by Lorentz, Poincaré, Einstein, Minkowski, Friedman, and Lemaitre. And these are the cosmology papers. These are the papers on special and general relativity. And you can sort of get about how these revolutions occurred, and they're absolutely here, and they are staying here with us. But how they occurred, how the leading people were thinking in wrong directions, and how they came to be accepted finally, etc. You can read about that, because it also has these original papers themselves, but with a longish introduction. Okay, so let me go to the last part, which is really ripples of space and time, which is gravitational waves. And I'm focusing on this, that other cosmologies, because LIGO India is a major project in which India will soon participate in actively. The project has been funded already, and therefore I thought this would be of interest to you. And again, it involves state-of-the-art technology, so it will also be of interest to people in engineering and technology in the audience. So the point is that I told you in the first part of the talk about general relativity. And in 1916, Einstein, just a year after the prediction of general relativity, used the weak field limit of his own equations, and then showed that in this limit, in this approximation, just as time-changing electric dipole produces electromagnetic waves, that is how X-rays, visible light, infrared, radio waves are produced. The radio waves, the radio station, there are really these time-changing dipole moments, and that is what is creating these electromagnetic waves that then we receive in our radio receiver up here. In the weak field limit of general relativity, in the same way, time-changing quadruple moment, if you have mass, which has a non-trivial shape, it has not only dipole moment, but a quadruple moment, then that produces gravitational waves. And it has 2 polarizations called H plus and H cross. If you have a ring of particles and a gravitational wave passes through it in a perpendicular direction to the plane that you're looking at, then to begin with, it may be all spherical or circular, as is written up here. And then if the ring of the gravitational wave passes in the direction perpendicular, then a quarter cycle later, this ring is distorted in this way. Then again, a quarter cycle later, the ring comes back to where it was. And then a quarter cycle later, it is distorted in this particular way, and then it goes back. So these distortions occur. That is one polarization. And then there is another polarization in which distortions are occurring at 45 degrees angle up here, as you see up here. And there are these detectors in the US, LIGO detectors. There are 2 of them in Louisiana and in Hanford, Washington state. And there is a detector also in Europe. And LIGO India is being constructed. And so LIGO India will join this. And that is why I'm talking about these gravitational waves right now. So the gravitational waves also have a curious history. And until about 1960s, there was a great confusion whether gravitational waves really exist in full nonlinear general relativity, or if they are the artifacts of a certain approximation Einstein made in 1916 when he drew these conclusions up here. So and surprisingly, Einstein himself contributed to this confusion. So one of these lessons that we see again and again is that even the greatest physicists of recent times, greatest physicist Newton, made many mistakes. And that's how science is. I mean, that doesn't diminish importance of Einstein at all, but he did make many mistakes. So surprisingly, Einstein himself contributed to this particular confusion. In a letter to Max Born, he wrote in 1936, he wrote a paper and he said that together with a young collaborator who was Nathan Rosen, this of course not young, is much later, Nathan Rosen, I arrived at the interesting result that gravitational waves do not exist, though they had been assumed to be a certainty in the first approximation. First approximation is the weak field limit that he had actually worked with. And then he says, this shows that nonlinear gravitational wave field equations tell us more, or rather limit us more than we had believed up to now. I mean, it's shocking that Einstein actually did believe that gravitational waves do not exist, even though he is the first, already in 1916, a year after the theory was born, he had this paper. And then he submitted the paper to physical review. Interestingly, in that year, in 36, he submitted 3 papers to physical review. And this paper was entitled, Do Gravitational Waves Exist? Arguing, as I said before, as I said in this transparency, that they do not exist, even though in a full general relativity, although they thought that, although he had shown, or and everybody assumed to be a certainty in the first approximation in the weak field limit, they thought they existed, but in the full theory, they don't exist. And Einstein submitted 3 papers to physical review in 1936. Oh, for some good intuition of the editor, only this paper was sent to the referee, and it received an 8-page report by Robertson. He is the one which is Robertson Walker Universe, the cosmologist. He wrote this 8-page report showing that there was a error in this paper of Einstein's, not in the solution itself, but in their conclusion. And Einstein and Rosen had curious reactions to this thing, namely that Einstein resubmitted the paper to Proceedings of the Franklin Institute. He withdrew angrily the paper from physical review, did not want to resubmit it. And he said that in any case, the referee is wrong. But then in the revised version, Einstein reversed the conclusion and even changed the title. And the title is On Gravitational Waves. The whole idea about gravitational waves don't exist disappeared up here. And the abstract is a rigorous solution for cylindrical gravitational waves is given. So it's very interesting for everybody to know that even, figures like Einstein do make mistakes, and one should not take everything that you hear for granted. And by the way, Nathan Rosen continued to believe the original conclusion that gravitational waves do not exist for several decades afterwards. But the resolution of the confusion came in the 1960s, so 30 years, actually more than 30 years later, due to Hermann Bondi, the British school, and Roger Penrose, and Ted Newman, and various other people. And then the reality of gravitational waves in full nonlinear relativity was firmly established only in the 1960s through systematic theoretical analysis by these people. And on the observational side, it was established by careful observations by Joe Taylor and his student Russell Hulse for a binary pulsar. So they observed a binary system, a star system, which is going around two objects which are going around each other, and their orbit is shrinking exactly by the formula that is predicted by the assumption that they're emitting gravitational waves. So they lose energy, and because they lose energy, their potential energy, which is negative, has to increase, and therefore their orbit becomes tighter and tighter, and that's what they observed, and they won the 1993 Nobel Prize for that. But the point is that one might ask, well, but why such indirect measures of methods of detection? Why is it that they had to observe some distant binary pulsar and they could not just directly measure gravitational waves on Earth at that time? And the reason is because the gravitational waves are extremely, extremely weak. The effective Young's modulus of space-time, gravitational waves are ripples in space-time geometry, and the Young's modulus is very, very rigid. It's about 10 to the 25 times that of rubber and 10 to the 22 times that of steel. And so space-time is very difficult to bend, and that is why you need extremely violent events that to shake the space-time geometry sufficiently to create ripples that can be observed. But the point is that it requires extremely good detectors, and such detectors have been created, and these are the observatories, and one of them would be set up in India very soon. It's called LIGO India, Laser Interferometric Gravitational Wave Observatory in India. And direct discovery of black holes and neutron star collisions has been made from now already in 2015 to 2020. There are 2 such observatories that exist in the world already, in the United States and 1 in Europe, so 3 of them. And they have observed these gravitational waves because these observatories require extreme sensitivity, and this sensitivity has been attained. And gravitational waves provide detailed images that we cannot obtain by electromagnetic waves, because electromagnetic waves are scattered as they are emitted from the source to up now. Because gravitational waves interact with anything else very, very weakly, they bring to us faithful images of what happens in these very violent events in the universe. And we have a brand new window on the universe now that could not even dream of in Newtonian gravity. So here is the direct detection on Earth. This is a triumph of human ingenuity. This is the first black hole merger. That was in 1915. And this 09 means September, and 24. So 24 September of 2015, not 1900, 2015, this event was observed, and it was loud, and it occurred on the very first day that the advanced detector was turned on. And it's luck, basically. And then since then, there have been, this is wrong, many more, actually, this is all transparency, many more subsequent black hole mergers have been seen. And there is also a merger of 2 binaries, 2 neutron stars, which are very, very dense stars. And they were followed by about 70 electromagnetic observations, because when the neutron stars collide, you still have visible light can come out of them. And they have been observed in many, many bands. And therefore, this really is a total revolution. And I'm very, very happy and proud that India is going to soon participate in this effort up here. So basically, I've skipped the birth of modern cosmology and the Big Bang. I just told you a little bit about the black holes just now, and I talked a little bit about gravitational I told you about black holes, and I told you about gravitational waves, and now I'll tell you about just a summary. So I just presented a few examples of paradigm shifts in fundamental science and astronomy. As this biologist, Edward Wilson, says, the physicists succeeded magnificently, but in doing so, they revealed the limitation of human intuition. Unaided by mathematics, an understanding of nature they discovered comes hard. The cost of scientific advance is the humbling recognition that reality is not construed to be easily grasped by the human mind. I mean, human mind operates on certain scales, whereas universe has scales which are much vastly larger than that, like length scales, mass scales, time scales, and also vastly smaller than that. And those cannot be absorbed very quickly by human mind. And paradigm shifts illustrate these paradigm shifts that occur, in the context of gravitational waves, in the context of black holes. They illustrate the audacity of human race to see way beyond what our senses can directly perceive. And so I could turn back to the first slide, and this is kind of really directed to you, younger people, young researchers, especially in this particular program that you are participating in. Namely, the paradigm shifts that I used offer some lessons for those of you who are working at the cutting edge of science. First of all, what is now considered as commonplace knowledge was not at all so just a few decades ago. In fact, most of the scientific community at the time was thinking in almost the opposite direction. So you have to keep this in mind. So if you have some original idea, which is kind of, you believe strongly, you have to have the courage to really pursue it. But I also want to add here that the reason why this is difficult is that you can pursue it, but once you have finished your analysis, you have to be your worst critic. And that is emotionally very draining. You have to really ask hard questions, but what I found, does it really make sense? And only taking this critical attitude, and if it passes that, then you can go ahead and publish it and believe in it. Secondly, precisely because they are so startling at first, the dramatic paradigm shifts take decades to get settled and become the new pool of knowledge. We're seeing this both in discovery of general relativity, then for the for the black holes, took a long time for them to be acknowledged, and finally for gravitational waves. It's more than 100 years since the birth of general relativity that these discoveries are being now fully acknowledged. And the third is that the factors driving or slowing the process are quite varied. It's not a matter of simple logical steps. I mean, you often feel, well, I showed this, and then why doesn't the world accept it? Because as we saw, world war can interfere, all kinds of things can happen, right? That's what happened with the First World War in an interesting way, in which actually the war people were hungry for something that is beyond the politics and insanity, and they wanted something objective like science, and that is why there was a real triumph of Einstein's discovery and Eddington's verification of that discovery. So enemy nations, if you like, German scientist and a British astronomer confirming a German scientist's predictions. So some dramatic things like that may be needed. It's not a matter of simple logical steps, as it is made to appear in the retrospect. So you need a maturity, so patience and this maturity. Finally, you need a sense of balance. I mean, you have to take the standard paradigms with a grain of salt and pursue what you believe. But as I said before, each time you obtain new results, however, you have to re-examine them critically. From my own modest experience, what I found is that this is the hardest part of doing science, namely to have the courage first, then predict something which is kind of unfamiliar, but then also be one's own critic, because you have invested so much time and energy into this work. But then you have to change gears, change your caps, and be your worst critic and try to see if in fact these ideas pass are worthwhile. They pass all the criteria, all the tests. Only then you can really create this paradigm shifts that I'm talking about. So I'll stop here and take any questions that you may have.
Thank you, Professor Ashtekar, for this wonderful talk and taking us on this sweeping journey from the singularity of the Big Bang to the singularity of the black holes. I have several questions for you, but I will confine myself to a couple of them, and then I will convey the questions from the audience. So I will start with the question that some of my students have asked me in the past, and I have tried to answer it in my own way, but I think you would be the right person to address this question. So does a gravitational field have energy density like an electric field?
Right. So there's no local energy density of a gravitational field, but there is a notion of energy because, for example, if you look at the gravitational waves, they can actually do carry. So it's ripples in the gravitational field, if you like, in the space-time geometry. They do carry energy. I mean, it's literally true that you could heat water with them. They carry energy. There's just no question about it. But in electromagnetic field, you can just locally you can say that I got energy density, E squared plus B squared, and momentum, which is E cross B. There is no such local formula for the gravitational wave, for the energy or momentum carried by gravitational waves. In general relativity, there is no such local formula. But they do, I mean, there's no local formula, but the total amount, I mean, if you have got some object which is changing quadrupole moment, it does carry away energy and momentum, and there are formulae written for them explicitly, like pointing vectors, if you like, but they are in a far zone. In the far zone, far away from the object, these formulae become unambiguous. I hope I answered it, but if not, we can, after the talk, we can continue.
Yeah, sure. So one more quick question. So we have had a couple of instances of observation of gravitational waves now. Have we tried to observe whether we see gravitational waves and electromagnetic waves from the same location and whether they arrive simultaneously? Because if they are simultaneous, if I understand it correctly, so we would be able to say that the postulated graviton would be massless, and if not, then it would be massive. Or is there some different understanding?
That's correct. So this event that you see on the right hand side of your screen is such an event in which you have to, when black holes, don't emit light, right? When black holes collide, there's no emission of light because light is trapped in that region. But when the neutron stars collide, there is actually also various, electromagnetic waves or light is emitted in various frequencies that comes up. And that is why this event was followed by 70 electromagnetic observatories in different different wavelengths, basically. And that one does see that they arrive within the observational error. The trouble is that there is an error bar, of course, with this observational error. This will improve in time, but they arrive at the same time. So they also travel at the speed of light, both gravitational waves and electromagnetic waves, with the accuracy that modulo these error bars, they are traveling with the same speed. That was a question, right?
Yeah. Thank you. So Dr. Suresh from Calicut, he's asking whether a black hole has its own lifetime as stars normally have.
Right. So, in classical physics, let me just tell you conceptually, and then I'll make a better statement. In classical physics, once a black hole is formed, it is just formed. And so it will just sit, it will just gobble more matter, or if there's no matter around there, then it will just sit there. But quantum mechanically, the black holes do evaporate. So there is a tunneling effect, basically, from which black holes will actually lose mass. And this is the very celebrated Hawking effect. So they really behave as though they're black bodies. But the temperature for a solar mass black hole is extremely small, something like 10 to the minus 7, 10 to the minus 8 degrees centigrade. So very, very small. But as the black hole shrinks, it has negative specific heat. And therefore, as it shrinks, its temperature actually rises. So small black holes will have a high temperature, and therefore the radiation from that would not be so weak. So the statement is that quantum mechanics does say that black holes will evaporate and they would actually emit radiation, which is approximately thermal, except in the very last stage of the black hole, which we do not fully understand. So the full answer is that once a black hole is formed, because of quantum effects, it will evaporate, but the time scales for this evaporation are very, very, very long, and many, many, many times the history of the universe.
Okay, thank you. Kalyan Roy is asking, he wants to know why, without spherical symmetry, a black hole is impossible to be formed.
No. Black holes does form without. No, sorry. Black holes can form without spherical symmetry. It is true that the particular solution that I referred to, which was due to Oppenheimer and Schreier, that was the first, 1930s when they found that solution. That solution, they assumed spherical symmetry. Yeah, 1939. That solution, they assumed spherical symmetry, but you don't need spherical symmetry. Completely general black holes will completely general stars actually collapse. They will collapse. Once they run out of nuclear fuel, they will collapse. And if there is, okay, so let me just be more careful here. If the mass of the star is less than about Chandrasekhar limit, which is 1.4 solar masses, then the statement is that there is still going to be electron degeneracy pressure, which is of quantum mechanical origin. And so light stars would grow into what is called as white dwarfs. They become very, very faint, but they're still stars. But heavier stars, this degeneracy pressure is too low, and the heavier star would actually collapse. And the statement is that the star doesn't have to be spherically symmetric at all. It generically, if it is heavier than the Chandrasekhar limit, then it would collapse, and it would, once its nuclear fuel is all burnt up, then it will collapse and form a black hole. So you don't need spherical symmetry. I conveyed a wrong impression if I did.
Okay, thank you. I just forgot to mention, Professor Godbole mentioned that in response to your answer that she will look up the paper that you mentioned. Yeah. One more question. I hope you have time, Professor Ashtekar, for there are several more questions that we have.
Okay, maybe let's go on for some time, and if it is getting very late, then I'll quit. But yeah, if the people still there and interested in questions,
so you can let me know when you have to leave. So I will stop at that point. Another 5 to 10 minutes, maybe.
Sure.
Is that fine?
10 minutes is fine.
Yeah. Okay. So Sushil Chauhan is asking, can we observe the event horizon indirectly or say something about it in observational data from LIGO or black hole image data?
Yeah, so we cannot observe it directly, but we can say something about it indirectly. And in fact, many people, including me, we're working on this thing. Namely, from the LIGO data, we could really talk about the dynamics of this horizon and what is happening there and so on and so forth. Because you can do on computer, using computers, one does simulations, and one can relate what is, theoretically, one can relate what you observe at infinity with what is happening on the horizon. So in that sense, we can actually detect what is happening on the event horizons, how the geometry is changing on the event horizon.
Okay, thank you. So one more question is from Akash Srini. So he's talking about how the Big Bang was formed 13.7 billion years ago, and how the universe emerged from a singularity Higgs field, and so on. And so he's asking how the universe could emerge from the singularity, which is a point of infinite density and gravity. And he's asking whether there is any point in talking about gravity and density without mass.
Right. So if you have density, then you can talk about mass in any given volume. So there's no problem about that at all. Talking about, if the total volume is infinite, and if you have got finite density, then the total mass would be infinite. But you can talk about mass. The question is about the Big Bang. So I think the general consensus, everybody's consensus, is that general relativity that I'm talking about here is an incomplete theory, because it's a classical theory. It ignores quantum effects completely. The point is that just as matter, if you like, its microscopic description involves quantum mechanics. So similarly, what Einstein taught us was really that space-time geometry is a physical entity. As we saw, it can be bent, matter can act on it, and because of sun, for example, here the space-time geometry could be bent, and then similarly the bent geometry acts on matter, like the planets, they move in this bent geometry, so their trajectory is different because geometry is bent. There's no force, it's just the geometry is bent, therefore their trajectory is different. So space-time geometry has this effect up here. Now the point is that with respect to the Big Bang, most of us believe that that general relativity is incomplete because it just completely ignores the quantum effects, right? And somehow once the matter density becomes comparable to what is called Planck density. So what is Planck density? Well, you can take fundamental constants of nature, and in this case it will be gravity, so there'll be Newton's constant, there'll be speed of light because there is also spatial relativity, and then h bar, the Planck's constant. And together, if I consider, I can put them together and obtain a unique quantity of dimension of mass, of dimension of length, and of the dimension of density. And one believes that once and also unique quantity for curvature. And one believes that once the curvature scale or the density scale exceeds this Planck density, then Einstein's classical equations are just not valid. You have to have quantum effects. So here, these are two-dimensional depiction of space-time geometry. It is bent, but it's still completely smooth. The idea is that just as matter has constituents, the space-time geometry itself has constituents. There are atoms of geometry. And what you need to do is to go beyond general relativity and talk about quantum gravity. And I have spent 40% of my time doing quantum gravity. And one of the approaches one of the leading approaches is really loop quantum gravity. The other one is string theory. And I worked on loop quantum gravity, in which we actually talk about, building up this approximate fabric of space-time from fundamental building blocks, which are quantum building blocks. So it's a bit like, looking at your shirt. If you look at the shirt from far away, it looks like a nice two-dimensional continuum. But if you just look at it under my magnifying glass, then it is not a two-dimensional continuum. You will actually see that it is built out of one-dimensional threads. That is just that the threads are so woven together so tightly that it, two-dimensional approximation, two-dimensional continuum approximation is good in most of the normal circumstances. The same thing is true with space-time geometry. Space-time geometry looks to us like a smooth continuum, but that approximation completely breaks down when you enter this Planck regime, where the matter density exceeds the Planck density, which is about 10 to the 94 grams per cubic centimeter, or the Planck curvature, which will be 10 to the minus 68 centimeter to the minus 2. So in that epoch, classical general relativity is just bad. It's just not good. And you have to replace it. And then there are various proposals of quantum gravity. And for example, loop quantum gravity has a proposal about what is the microscopic building blocks. And these microscopic building blocks are one-dimensional threads. They're like, and it's basically like under normal circumstance, like my shirt, just as my shirt is built out of threads, but you can think of it as a two-dimensional continuum. Similarly, space-time geometry is built out of these one-dimensional quantum excitations, one-dimensional quantum threads. But under normal circumstances, it gives you an illusion or approximation of a four-dimensional continuum. But this approximation breaks down. So basically, I agree that the idea that everything becomes infinite at Big Bang and comes out of that is not really plausible. You need a better theory. It just is telling you that general relativity is failing. And quantum gravity, particularly, for example, loop quantum gravity, is precisely its aim is to go beyond general relativity and see what really happens there. And in fact, what we find is that there is no singularity. Space-time doesn't end at the Big Bang. The quantum space-time still continues, so to say. And you can't talk about the past Big Bang branch of the universe, etc. But it's a whole new topic, and that is why I did not enter into it.
Okay. Just 2 or 3 more questions and then we will stop. So Dr. Ajit Maurya is asking, what is the major goal of LIGO India? And it goes along with a question that I had, that where does India stand with respect to LIGO at the moment?
Right. So what we have currently for gravitational wave detectors is really 2 LIGO detectors in the United States and 1 Virgo detector in Europe. Now, the Virgo detector arm length are only 2 kilometers, LIGO detectors are 4 kilometers. And so, the LIGO detector is more sensitive than the Virgo detector. Now, what would happen in India would be a 3rd detector, right? Which will be the LIGO India, 4th detector, which will be LIGO India detector. And that, the importance of that detector is really that it is, currently all the detectors are in the northern hemisphere. Now, India is also in the northern hemisphere, but it's closer to the equator. And because of that, you would get a somewhat better resolution. You will be able to, the network of these detectors will be able to say the distance to the source, where the source is, so to say, more accurately with 4 detectors. And especially because of the location of India, it's the Indian detector, what is called the polarization measurement will be much, much improved. And that is an important aspect in extracting physics and astrophysics. And so the statement is that with LIGO India, we would be able to really enhance the accuracy and predictive power of gravitational wave astronomy. And therefore, the whole world is sort of waiting for this thing to come online, hopefully soon. I should say that there is another detector, which is in Japan, which is already essentially online, but we'll start taking data very, very soon. Kagra. But I think LIGO India has but it's also in the northern hemisphere. So I think the LIGO India detector would be very, very good. The next question is where are we? Well, I think before this COVID hit us, right? I mean, LIGO India budget was completely approved, and the the main funding agency is coming through Atomic Energy Commission. They have very good lot of practice, lot of experience with large projects, management of large projects. So it is most appropriate. And they have a site and the construction should have begun, but I think because of COVID, it is delayed. So I think I still hope that it will come online in 27. So 2027. So it's about 6 years from now. And then our localization of where the source is located will improve enormously. That would be a very, very, very good thing. And the polarization measurement will also improve, and we'll be able to extract much more astrophysics of the sources from that.
Thank you. So I have just a couple of more physics questions. I will convey them both together. So what are the problems one faces in quantum field theory when we try to generalize it to curved space-time? That is one question. And there have been several questions asking about do multiverses exist? So would you like to comment on the two questions?
Yeah. I was just writing them down. Okay. So in quantum theory in curved space-time actually is very well developed by now. What happens is the following: in curves, in Minkowski space, in flat space-time, when we have quantum field theory, then we use very strongly the flat metric on which these fields propagate. In a curved space-time, the fields also propagate on a smooth geometry. This is a quantum field theory in a given space-time. It's not quantum geometry proper, quantum gravity proper. Therefore, the space-time geometry is taken to be classical, to be smooth, and various quantum fields propagate on that. So the difference is basically that in one case, in the flat space-time case, we got a lot of symmetries. The whole Poincare group acts, and that enables us to zero in on some representation of the canonical commutation relations. Let me just backtrack a little bit. In ordinary quantum mechanics, we have got a unique theorem, a uniqueness theorem due to von Neumann and then Stone, which say that if you look at the Heisenberg or its exponentiated form, the wild canonical commutation relations, then there's unique representation on them of them, which has some technical continuity properties. And that is a representation, the Schrodinger representation that we use all the time. In fields with infinitely not many degrees of freedom, this is not the case. In the fields with infinitely many degrees of freedom, if you just start with the canonical commutation relations or their exponentiated versions, wild commutation relations, they still admit infinitely many representations. That means that there are infinitely many Hilbert spaces and infinitely many ways of representing operators, field operators as concrete operators on this Hilbert space, which are inequivalent. Mathematically, they are inequivalent to each other. But the presence of Poincare group helps enormously in cutting down that freedom. And then we have got basically a unique way of talking about quantum fields. I mean, in terms of Hilbert space and the upstates and the operators. In curved space-time, we don't have that because there are no isometries, there are no symmetries. If space-time happens to be time independent, so stationary, then again, you've got a uniqueness theorem. You can just work with one representation, one Fock space. But in general, we do not have that. And therefore, there's a choice to be made about which representation you should use. In cosmological context, one has some ideas about good reasons to work with certain representations, not others, or one can develop techniques which really don't depend on choice of this representation, the canonical commutation relations. You can have distinct Hilbert spaces and you can still make physical predictions. So the quantum field theory in curved space-times is in good shape. It is not as tight as quantum field theory in Minkowski space-time, but one understands the physics of it quite well, and people use it routinely. For example, the entire work on inflation and or its replacement. Almost all work in cosmology in the very early universe uses quantum field theory in Kerr space-times, and that is quite well developed. The next question was about
multiverses.
Multiverses. I mean, this I really don't understand them. But now I'm just making a personal statement. What I was saying before is my personal statement, as well as the general consensus in the field about quantum field theory in Kerr space-time. With multiverses, I personally don't understand the detailed logic behind multiverses up here, because people typically don't write down the entire space-time diagram with the causal structure that is given in that is there for these multiverses. One just sees bubbles and so on and so forth, but one doesn't see what the space-time diagram there is. So I don't kind of feel that multiverse is on such a, this is my personal view, that is on such a solid footing. I mean, if one just says that, and what is on solid footing is the following: if there is a small cosmological constant, positive cosmological constant, which there seems to be, it doesn't have to be small, but it happens to be small, then certainly any one observer will only see part of the infinite universe. No matter how long you wait, there are parts which will be completely invisible to you. If by multiverse one just means that, then I understand it completely. But then the point is that for any one observer, there is only one eternal observer. There's going to be only one universe, and then one can make those predictions. It is true that different observers might see different things in their causal past, and the predictions will be different. But for any one observer, there will be, or for any given set of observers rather, there will be only unique prediction. But people draw these various diagrams, in which with bubbles and going around and such thing, and I never see what the light cone structure of those diagram is in sufficient detail to really understand what is being claimed. So in my understanding, there is a little bit of vagueness in this whole notion of multiverse. I know very distinguished people talk about it, but I really feel, I asked several of these people these questions, and I've not gotten a satisfactory answer to that.
Thank you. I should mention that these questions were from Aryadeep Paul and Nidhishwar, the two questions that I just asked you. One final question from Dr. Anand Hota. He's asking that paradigm shift research is probably possible in theory, but how would one try it in experiment in a resource-poor environment like universities in India? What would be your
what research? Advanced research or no? What is it?
No, he's asking about paradigm shift research.
Paradigm shift
is perhaps possible in theory, but how would one try it in experiment in resource-poor environment like universities in India?
I agree. It's much more difficult, and I know the examples I gave in the beginning did come from theory, like these black holes. I mean, it took there were theoretical predictions first, but it required ingenuity of the it really required, where is here it is. It really required ingenuity of these people, experimental observations, to really talk about, to be able to develop advanced, sufficient technology to be able to image the center of the galaxy properly. And the same thing is true with LIGO and Virgo, where advanced technology is absolutely essential. So my kind of answer to that is the following, that in the areas that I have talked about, the only way would be to actually join one of the collaborations, right? Like LIGO India collaboration. And in that collaboration, you would still be able to, I mean, because that does provide state-of-the-art technology, and you would be able to actually create some new ways of observing that might change the paradigm. This paradigm shift, for example, is already occurred, right? I mean, people typically believe that either you got black holes of a few solar masses, like 3 or 4 solar masses, or or 5 solar masses, or you got these supermassive black holes in the center of galaxies. Not many people expected that there will be black holes of tens of solar masses, 100 solar masses, but they have been detected. So you can, both in terms of software development, writing the ingenious codes and so on, and in terms of uh, adding to the current available technology and LIGO detectors and so on and so forth, you could contribute to paradigm shift. But on the other hand, in something like condensed matter, tabletop experiments, there I think one can contribute to paradigm shifts. They are not of the paradigm shift that I am talking about, but one could actually do experiments in the local observatory, local laboratories to create those paradigm shifts. I have to confess that I don't have. I mean, I'm in contact with Indian science quite a lot. I come and visit and so on, but I'm not in so much contact with things like in what is happening in the university environments in quantum optics, for example. I do know that that in Indore, the Center for Advanced Technology in Indore, for example, they have enough resources to create these things. So I don't know if it's possible to be associated with one of those groups or something like that. Unfortunately, I cannot give a good answer because I do not have a good idea about what is available in condensed matter physics and atomic and optical physics in order to work to work towards on experiments that can cause paradigm shifts. I only know that in Indore, the Center for Advanced Technology, they do have resources that can create these paradigm shifts.
Thank you, Professor Ashtekar, once again for your patience in putting up with so many questions. Now I request the Secretary of the UFA, Dr. Supriyo Das, to give the vote of thanks.
Hello. Hi, it is my privilege to propose the vote of thanks here. I, on the behalf of the UCFRP's University Faculty Association, and of course on my own behalf, would like to extend a very hearty vote of thanks to Professor Abhay Ashtekar for delivering this very interesting talk and enlightening us on black holes. We have been quite fortunate to have Padma Shri Professor Rohini Godbole as our guest of honor. I personally thank ma'am for giving us the giving your thoughts to us, and I take the opportunity to thank Dr. Sujit Tandal for coordinating this event. I want to extend my generous thanks to President of University Faculty Association, Dr. Harish Gupta, the executive committee members, and all members of our association for making this event a success. Finally, I would like to thank our participants, and I hope that we all will be together very soon in a similar event near future. I hand it over to Dr. Tandal without spending much time on it.
Thank you, Supriyo. And thank you once again, Professor Ashtekar and Professor Godbole.
Can I just make one small remark? Can I just,
sure.
I mean, in case you are sort of curious about what is in the background of my screen, that is actually the statue of Einstein in front of the National Academy of Sciences. And Einstein is holding kind of a sheet of paper. So you see on the left-hand side up here, Einstein's hand, and this is a sheet of paper. Of course, it's a sculpture. And these are the three main equations that Einstein discovered. So I just wanted to clarify what that thing was. It's a statue which is just created on the Einstein's centenary of Einstein's birth. Okay, that's it.
Yeah, thank you, Professor Ashtekar, and thank you, Professor Godbole, for being here, and thank you to everyone who participated, both on Zoom, and we still have more than 100 viewers on YouTube. So we will be back next month with the next lecture in the series, which will be announced shortly. And I wish everyone a good night, and wish you a good day, Professor Ashtekar. Thank you. So we'll end the meeting here now. Thank you.
I think it was really good. We had more than 2 hours discussion, lecture discussion, and it's really good. So I think congratulations to you for putting best efforts. And
No, I
I
mean,
think
we
on
are
YouTube
glad,
also,
yeah, we were fortunate to have a good speaker and a good chief guest, and so
yeah, and YouTube also I think is a good idea, and we had almost, I think it reached up to 140 people, 140,